Well, hello again. Today we're here talking about the motions of the slide that you see now is of a camera that has been turned toward the north celestial pole. That's where Polaris is. Polaris happens to be this little arc. I'll point my arrow at it. And this is what occurs when you take a photograph of the sky, not in a single fraction of time, but rather it occurs over a long period of time, a time exposure. So in this case, the camera was opened and the light fell on the film for a long period of time so that there were star trails made. And as we talked about in the planetarium, the farther something is north, the longer it stays in the sky. Notice that these stars that are right around the celestial pole just make circles around the celestial pole. And these other stars that are farther from the pole, the circles are bigger. And in some cases, the stars are so far from the pole that the horizon intersects with them, and so they set. So this region around the north celestial pole, these stars never set. They're always in the sky, but the farther one gets from the celestial pole, the stars eventually set. So the farther south something gets, the shorter period it happens to be in the sky. So this is a time exposure of the stars near the north celestial pole. The constellations are merely convenient ways for us to talk about the sky, like the names of a street signs, and by reading them. Constellations, however, are really, that word describes two things. It describes the familiar pattern of stars. For this case, it happens to be Orion, the hunter, 3 stars in a row that make his belt. The star Betelgeuse, named over here, makes his shoulder, and one of the bright stars marks his knee. So Orion happens to be the pattern of stars that we're familiar with, and it also happens to be a part of the sky, very much like an outline of a county or an outline of a state, has its own distinct regions. So Orion, the hunter, is not only the familiar stars that we know, it's really a patch of space that is around those stars, much like a piece on a quilt, a patch on a quilt, or an outline of a state. In the sky, we make measurements using angles, and your hand is a convenient measurement device. For example, your fingertip, if you hold your hand at arm's length, your fingertip covers just about 1 degree. So if you have a big hand and a short arm, or whatever the case might be for you, it's about an average of your fingertip, your index finger, covers about 1 degree. And 1 degree is about the diameter of 2 moons. The full moon is about 1/2 degree, the full circle. And in this case, this is 1 degree, so it's about 2 moons. And the sun happens to be about 1/2 degree as well. So across your hand is some 10 degrees. And if you look on this case, you can measure some other angles by the knuckles on your hand. They can make measurements too in the sky, but about 1 degree for a fingertip. You can easily cover the sun with your fingertip out at arm's length. So we use these angles in the sky to make measurements, because we don't know how many miles away, and on the celestial sphere they all look the same distance away. And so what we have here is the way of measuring distances, separations, are in angles. In this case, the Big Dipper, these stars here happen to make the Big Dipper pattern. And the 2 stars at the end of the Big Dipper that we referred to as the pointer stars, these 2 stars here, are approximately 5 degrees separation. So that's 5 degrees. That would be 5 fingertips held up at arm's length, make the separation between the stars of the bowl of the Big Dipper, the pointer stars, as they are known. The sky itself can be represented by this celestial sphere. It is imaginary. It's not real. It is very big in size, infinite in size, and it's much bigger than the. It's much bigger than the Earth. Although we have to represent the Earth in here, we just couldn't represent it as a dot. So we have the Earth at the center. We happen to have the celestial poles that are directly above the Earth's North Pole and directly above the Earth's South Pole in space. They're directions in space, not necessarily real places. And we have the celestial equator. Which is directly above the Earth's equator. And we have angles that are measured along the equator. That's the right ascension angle. That is your line of longitude. And your line of latitude is declination. It's how far north and south. So right ascension is measured in hours and minutes, much like time, except it's an angle, so that 1 hour of time equals 15 degrees. And declination is the distance north or south of the equator, and that is measured in degrees. So we have right ascension and declination are the ways that we make measurement of the angles in space measured along the equator for right ascension and north or south of the equator for declination. These important terms on the left, the vernal equinox, is the origin point. That is the place where we have 0 hours of right ascension and 0 hours of declination. So the right ascension is measured along the equator, that line directly above the Earth's North Pole, or the definition here is the line separating the celestial sphere into northern and southern halves. There can be many of those, but the key is northern and southern half, and the declination is measured north above or south below the equator. That happens to be the declination. During the night, the celestial sphere, and during the day, it seems to rotate. However, this is really caused by the Earth's rotation. And star trails, again, when you look at them from a time exposure from a photograph, you get this. And these stars are setting. These are setting stars. We're looking west, and notice that the stars are moving parallel to the equator, and so the equator is rising up at an angle. And remember from our planetarium visit that this angle with the horizon is equal to 90 degrees minus your latitude. And in this case, these stars are setting because they're going this direction, and we are looking west. We're looking west, and that's what the sky looks like when you're looking west. The sun sets and the stars set down to the right angle, and so this is the latitude. With a protractor, this is the angle it sets at. With a protractor, you could actually determine the latitude of this spot by holding that protractor horizontal on here and then measuring the angle. You could measure that angle subtracted from 90, and you would get the latitude of this particular location. We're not trying to do a lot of math, but this is an example of how one from a photograph can determine where they are by looking at rising and setting stars. As I briefly mentioned in planetarium, sometimes it's possible on TV shows when they get a little lazy, or on a movie where they'll photograph a sunset. The sunset will do the same thing. It will start setting this direction and will go beneath the horizon. And so sometimes you'll see the sun in some TV shows or movies where they photograph the sunset and then they make it rise. And so, in other words, it comes up out of this angle like this. However, when the sun rises, for us here in the northern latitudes, it rises up this direction. And this is what happens in the eastern sky. And in the western sky, the sun and stars are setting down in this direction, not in the direction that the TV shows sometimes do when they get a little bit lazy in trying to do that. Now, as we go from different locations on the Earth, the sky obviously moves different because sample changes of setting, rising and setting stars change. So, for example, if we go to the North Pole, a nice polar bear there in this picture. If we go to the North Pole, the celestial pole is going to be straight up, and the celestial equator is going to be right here on the horizon. So all of the stars are moving parallel to the horizon as the Earth rotates. So remember, 90 minus the latitude, 90 minus 0, or 90 minus 90 rather, equals 0. And so here the angle is 0 degrees, and all the stars are moving parallel to the horizon. At the equator, it's quite different. At the equator, the stars move perpendicular to the horizon. Notice here the angle is 90. So here's where you get 90 degrees minus the latitude, which is 0. And so these stars rise and set. Everything at the equator rises and sets perpendicular to the horizon. So you can tell the location on Earth. Again, another navigation point is noting the way the sun rises and sets. The stars rise and set. You can tell your latitude. But the challenge for a considerable amount of time for those mariners was, where were they in longitude? Where were they on the Earth's surface? The other very important line is the ecliptic. This is where the sun seems to move on the celestial sphere throughout the entire year. It moves a little bit each day, seems to move a little bit each day, caused by the Earth's rotation. So now, adding the celestial equator and the poles in the Earth, we now have this ecliptic that is has an angle of 23.5 degrees, which is the Earth's tilt. And we have these very important points in the sky, such as the vernal equinox. The vernal equinox is where the sun's coming north. We have the highest point, which is the first day of summer. This is called the summer solstice. On the other side of the sphere, where the sun appears to go south of the equator, this is the first day of autumn, sometimes referred to as the autumnal equinox. And the low point, which is for us, we refer to it as winter solstice. Now, in the southern hemisphere, this is the opposite. Seasons are opposite south of the equator. So this could be considered the June solstice rather than the summer solstice. And this could be considered the December solstice rather than winter. It's the first day of summer in Australia. It is the first day of winter for us. So the ecliptic is the sun's apparent annual or yearly, annual, A-N-N-U-A-L, annual yearly path across the sky. These are the ecliptic, and these are the ecliptic, which is caused by the Earth's tilt. Here is another Here is another chart that shows the same. So if you want to see this a little bit differently, you see the important points are now added in: vernal equinox, the summer solstice, these important directions in space. So as the sun seems to move on the ecliptic, we seem to get these, or we do get these apparent differences in position in the sky of the sun. And these are not quite exaggerated enough, actually, where we have the highest point on the first day of summer, the midpoints at the equinoxes, and the solstice position, the winter solstice position, when the sun seems to be lowest in the sky. And so each day, then, the sun makes a different arc across the sky, changing ever so slowly each day. But then throughout the year, there's an obvious change from the high point of the first day of summer, from the high point on the first day of winter. Similarly, there's another small issue caused by the Earth's shape, the Earth's orbit's shape. The Earth's orbit is not a perfect circle. Rather, it is slightly out of round. And we'll talk a little bit more about that shape later in the class. But what happens is that when you photograph the sun, in this case every 2 weeks, at the same time, you get this shape. Notice that here is the summer sun. Here is this one is the equinox sun. And this one's the winter sun. So this strange shape is commonly called the Analemma. Name you don't have to know, but it's called the Analemma. As the Earth revolves around the sun, because the Earth's orbit is not a perfect circle, the sun seems to has this slight difference. At the same time each day, the sun is in a slightly different place. You would expect the sun, if the Earth's orbit were a circle, to be somewhere along that line, but sometimes the sun is faster than where it should be, or it's a little slower than where it should be, and that's caused by the Earth's out of round shape. The sun is not Earth is not in a perfect orbit's not a perfect circle. Now, as the sun is sometimes high and sometimes low, it impacts our climate, impacts our weather. When the sun is really high, the sun's heat and light is really concentrated on the ground. And the ground gets warm, and plants begin to grow, and we get the warmer days of May, June, July, August, spring, and summer. But as the sun seems to be lower at noon, the sunlight is spread over a wider area. It's more difficult to warm the ground, temperatures drop, and snow falls rather than rain. And this is caused by the sun's position in the sky and its warming effect. When the sun's really high, like in June and July, its warming effect is very strong. And as the seasons progress and we get into December and January and February and November, the warming effect is much weaker, and so we get winter out of that. So the seasons are caused by the sun's position in the sky at noon. The celestial sphere, if we go back to that for a moment, we go back to a celestial sphere. Here's one that you may have seen in the video separately, but this celestial sphere, briefly come back to it, and let me cut that celestial sphere open for a moment and get this chart. This chart that forms the equatorial region of the sky, where you can see the difference see the difference in the in between the equator and the difference in the ecliptic. So the line that is sort of wiggly here is the ecliptic. That's the sun's path throughout the year. And the straight line across here, this line, is the equator. It goes all the way across the page. And over here, you can barely see that it's named the equator. So we have the ecliptic and we have the equator. The point that is actually on both sides, which would be the 0, point, 0 hours of right ascension and 0 hours of declination, on the right side is here and actually repeats itself on this side. So that's the vernal equinox. The autumnal equinox is this direction. How do we know the difference? Because the sun, the sun is, let me try this again. This is the autumnal equinox. The sun is going this direction on the ecliptic, and this is where it's going south of the equator. And these other 2 points is where the sun is going north of the equator. So we have the summer solstice, and we have the winter solstice. Those days are marked by the sun's coordinate, those instants of time. The vernal equinox is declared by astronomers when the sun's right ascension is 0 hours, its declination is 0 degrees. The first day of summer is declared when the sun's right ascension is 6 hours and its declination is 23.5 degrees. The first day of autumn is declared at the moment when the sun has a right ascension of 12 hours and a declination of 0 degrees. And winter is declared 18 hours right ascension and negative 23.5 degrees of declination. That is when astronomically those events occur. And sometimes the weather is not exactly matches the solstices and the equinoxes. Typically, for example, in summer, the longest day, in other words, more sunlight than other days, is around June 21st. For weather, the hottest day of the year is typically about a month after that, and the same occurs in winter. The coldest winter days are usually in late January, historically, although the first day of winter is at the end of December. So these are the astronomers' definitions of the first day of summer, the first day of autumn, the first day of winter, and the first day of spring. And as we've mentioned before, these places are where we can make measurements of the coordinates of objects because it becomes an easy way to communicate. It's like an address. The city's longitude and latitude, it's very easy to then communicate a location. Please take a look at this archive as you need to. Take a look at the assignments for the week and get them turned in a timely fashion. And thank you, and communicate with me as you need to.